Apologize for our problems, technical. Please start.
So I think it is my problem.
So Vladimir, you can start. Please start.
Okay, thank you. And thank you very much for my invitation to give talk in this nice conference. Okay. Okay, my talk is devoted to n-dimensional n larger than 2 Dirac operator with singular delta potential supported on hypersurfaces in array. In dimensional 3, such operator arise in problems of confinement and transition of relativistic particle through surfaces that are supports of the singular potential. The formal Dirac operator with delta singular potential is the sum of the regular Dirac operator and the sum singular potential, where the regular Dirac operator is the standard Dirac operator with the magnetic potential, the variable mass with the electrostatic potential, where the alpha with point means the sum of the product, where alpha entonces я не могу переключить это самое. Ага, окей. Where alpha G are the Dirac matrices that n by n Hermitian matrices satisfying the anti-commutative relations. E is the unit matrix, E n large is connected with the dimension of the space by means of this formula. A as magnetic potential, M is the variable mass of the particle, P is an electric potential. Gamma delta sigma is the singular potential, where gamma is the n by n strength matrix. Delta sigma is the delta function with support on a hypersurfaces sigma belong Rn, which the common boundary of the set omega open set omega plus omega minus. We assume in this moment that the potential belong to the space of the continuous bounded on Rn functions. Gamma as bounded function on the surface, and sigma is a C2 surface, which can be bounded and unbounded. HRP be the space of the vector valued Bessel potential, HRP omega plus minus be subspace of the restriction of the distribution from HRP on omega plus minus. We denote by BRP the Bessel space on Rn, and by gamma plus minus is the sum, the operator of the trace acting from HRP into the Bessel space on the hypersurface sigma. We say that C2 hypersurface sigma is uniformly regular if for fixed R and each point Y there exists a ball and diffeomorphism such that the following condition holds. So the image of intersection of R E sigma as intersection of the unit ball with the subspace Rn -1 image of the intersection. This intersection is intersection unit ball from half spaces. We suppose that all derivatives, this mapping is uniformly bounded. Note that the compact hypersurfaces and many unbounded C2 hypersurfaces are uniformly regular. We associate with the formal Dirac operator the unbounded operator, the calligraphic in the Hilbert space L2 Rn defined by the Dirac operator with the domain. With the following domain. So it's is domain in the Sobolev spaces H2 with condition with the sum interaction condition by sigma S equals 0, where interaction condition has the following form. So this interaction condition can be obtained by means of the integration by parts and the remove of the singular part of the operator. In this case, coefficients A plus minus S is has the following form, where it means that the sum of the production of the Dirac matrix by the coordinates of the normal vector at the point S and the point S. Nu S is the normal vector. The first result which obtained is the theorem about self-adjointness of the operator, this operator. Let sigma be a C2 uniformly regular hyperspace. Gamma is the matrix components which belong CBRN and gamma S be Hermitian matrix for each S belongs sigma. Is a uniform Lopatinsky condition. It is analog the usual boundary Lopatinsky condition. Hold. In this case, this Lopatinsky condition, uniformly Lopatinsky condition, has the following form, where the S sigma is a cotangent space to sigma. If this condition is satisfied, then the operator dA phi m sigma is self-adjoint. So, of course, this theorem take place in the case of the sigma is enough smooth and regular hypersurfaces. So this theorem works for the compact C2 surfaces and non-compact C2 surfaces, which is uniformly regular. we consider in the talk also the operator of the interaction, the transmission problem associated with the formal Dirac operator. This interaction transmission problem defined by the Dirac operator on Rn minus sigma and the boundary condition, where the boundary transmission is more correct. Transmission operator B sigma is defined above defined. This operator is bounded in the space H1P minus sigma into the space LP plus BP1 minus P the spaces on the boundary sigma, We will consider in the talk the Fredholm property, the interaction problems for compact and some non-compact hypersurfaces sigma. We need the notation. I denote by S01Rn the space of the differentiable function with bounded differential function such that the partial derivatives tending to 0 fx tending to infinity. The function of this class are called slowly oscillating infinity. Let us consider, first we consider the interaction problem on where the sigma S is the compact. In this case, we proved the following theorem. Let the coefficients, the magnetic potential, variable mass and the electrostatic potential belong to the slowly oscillating at infinity. Sigma is sigma close C2 hypersurfaces, and the interaction matrix has elements which belong to the space C1 sigma. Then this operator is the Fredholm operator if and only if the Lopatinsky-Shapiro condition hold for every point of the hypersurface sigma. The Dirac operator is locally invertible at infinity. It means that in some sense the restriction of the operator on the exterior of the ball in a large radius has the left and right the local inverses. Condition of the local invertibility at infinity is equivalent to the condition. This condition may be noted as a condition of is the elliptic condition at infinity. So this condition is considered for limit infinitum this determinant of this function. Determinant of this function in infinitum with respect the variable psi larger than zero. Condition 5 in this case of the Dirac operator, in this case of the Dirac operator, following from the this condition, this condition, where m is the variable mass and phi of x is the electrostatic potential. We consider also the Fredholm property of the interaction operator on the some unbounded hypersurfaces. This hypersurface is slowly oscillating at infinity. So definition is the following. The sigma has the following definition. Xn S equal f x prime, where b prime r is the exterior in Rn minus 1, the ball of the radius r, where the function f belongs C2 is a real valued function with the following property. Limit the second partial derivative, if x prime tending to infinity is equal 0. In this case, we say that the sigma is slowly oscillating hypersurface at infinity. This is enough general example of the function f. So the function f it has the following form: x prime alpha, where alpha multiply for the function q, which defined on the unit sphere, which belong the space C2, which is to smoothness, alpha smoothness, and alpha and beta belong to the interval 0, 1. And once by means of the calculation, we can obtain that this condition holds. So important example, sigma. Sigma is a conical hypersurface at infinity. Sigma can be parabolic hypersurface at infinity. E and more. This is the hypersurface. Can be oscillation at infinity. We define by the multiplication by the sems. The following theorem gives the conditions of the Fredholm of the interaction operator. We suppose that this condition holds, so the potentials are slowly oscillating at infinity. This hypersurface sigma is B2 hypersurface, which is slowly oscillating at infinity. E strength matrix has the coefficients which belong to which are slowly oscillating at infinity. Then the operator this operator D is a Fredholm operator if and only if the Dirac operator D is locally invertible at infinity. The Lopatinsky-Shapiro condition satisfied, and each point S belongs sigma, and the sum condition at infinity hold. So this condition at infinity is following: limit infinitum, determinant, the symbol sigma x prime psi larger than 0, where sigma x prime is the point of the sigma, which has coordinates x prime f x prime. The sigma x is the cotangent space to sigma at the point sigma x prime, and the symbol sigma x prime is the matrix valued symbol which has the following form, We also consider the integral equation method for the interaction problem for Dirac operator, interaction problem for Dirac operator. So we introduce, we assume that the Dirac operator, this Dirac operator is invertible. So this operator, we can in the case of the M and P are constant, and P are constant, we can obtain the effective condition of the invertibility of this Dirac operator. But for me, in this moment, is enough that this Dirac operator is invertible. The operator dmp minus 1 is a pseudo-differential operator of the class of operator S minus 1, 1, 0, with slowly oscillating at infinity symbol. Moreover, this operator has some integral representation where this function belongs to infinity and has the following estimates. So it is infinitely differentiable outside the diagonal and has the exponential estimates if module x minus y larger than 0. So we introduce the potential operator. In the following. The property of this potential operator is the following. This operator is bounded from the sigma in the space H1P Rn minus sigma. There exists the non-tangential limit. There exists non-tangential limit where the Kpm sigma is the sum is a Calderon-Zygmunt singular integral operator with the principal symbol which has enough simple form. We will look the solution of the interaction problem. This interaction problem is the following form. Substituting U given this formula in the interaction condition, we obtain the integral equation on sigma in this space. this this space, where the this space, this space. So the next theorem is connection from the solvability of Fredgovness of the interaction problem is of this integral equation on sigma. Assume that M phi belongs to this class. Sigma is a closed C2 hypersurface. Gamma belongs this space. The operator the M phi is invertible. Then the operator of the interaction problem is a Fredholm operator if and only if the singular integral operator on the hypersurface sigma is Fredholm. The last condition, the Fredholmness of the singular operator on this singular integral operator, given the
4 minutes left. 4 minutes.
The Lopatinsky-Shapiro condition. Given the Lopatinsky-Shapiro condition. And the similar result is obtained for the interaction on slowly oscillating at infinity hypersurfaces. So in this case, we suppose that M phi belongs as this space. Sigma is C1 hypersurface slowly oscillating at infinity. Gamma satisfied to this, and the operator the M phi is invertible. Then the M phi is the Fredholm operator if and only if the operator on the integral operator on the hypersurface sigma is a Fredholm operator. Thank you very much for your attention. This is all.
Thank you. Thank you very much. Are there any questions or comments, please? Just go ahead and ask. I don't see raised hands yet. Well, I have a question. So how do you define the Dirac operator? Because it has this singular delta potential.
Definition. This is a formal operator. The Dirac operator with the delta interaction is a formal operator which sometimes exists in many books in the quantum mechanics. But in general, we consider this operator, this singular operator, we change this singular operator following to the Berezin-Faddeev to the sum unbounded operator. So in general, we consider the sum unbounded in the sum interaction problem with connected with the sum formal Dirac operator.
Okay. Are there any other questions or comments, please? Well, I don't see any, so thank you very much again.
Thank you very much for your attention.
Okay, so how should we proceed? Should we start right away, or should we have a short break?